Hi everyone. So today's lesson is on real numbers and number operations because I think it's really important for us to discuss the different types of numbers that we're going to be dealing with this year. All right, so when we're talking about real numbers, there's actually a symbol that you'll often see. Printed, it looks like that, but if I'm going to draw it, it looks like an R with two lines through it. This means that we're talking about all real numbers. All real numbers. Yes, and there's some other types of numbers called complex numbers that we're going to get into later this year. But let's talk about the subsets of real numbers. The first subset are the numbers that you learned naturally, I call it. The first number you probably ever learned was the number 1. So the natural numbers cover from 1 up. Now they're all whole numbers, so 1, 2, 3, and so on. And then eventually, there was a need for the number 0 when we talked about nothing, because nothing represents something in math. So when we added 0, now we have a new set of numbers called the whole numbers. Again, still completely whole, no fractions, but starting at 0. Now, so far this year, we've talked a lot about the term integers. Integers are incredibly important, and integers brought into this idea of a negative. So integers are positive and negative whole numbers. Okay, positive and negative whole numbers. So -2, -1, 0, 1, 2, and so on in both directions. That term's used a lot on standardized tests because they'll ask you, for the following integer. So you really want to make sure you understand that an integer cannot be a fraction or a decimal. All right. In the coming weeks, I'm going to be spending a lot of time talking about the term rational numbers. A rational number is any number that can be expressed as a fraction. Any number that can be expressed as a fraction. Well, to be quite honest with you, natural numbers can be expressed as a fraction, whole numbers can be expressed as a fraction, and integers could be expressed as a fraction. I could do -2 over 1. I could do 3 over 3. So all of these are rational numbers. But let's talk about numbers that can be expressed as a fraction. 2/3, -3. I don't know, 0.3 repeating. So rational numbers also, in your mind, I want you to think of them as terminating or repeating decimals. Okay, terminating or repeating decimals. Okay, so let's talk about that for a second. You should actually know that 0.3 repeating actually is the fraction 1/3. 1/3 works out to be 0.3 repeating. And we're going to go over some more fractions that I think are important for you to know this year. But right now, rational numbers terminating or repeating decimals. So 5.7, that is a rational number because I can write that as 5 7/10. I can express it as a fraction. Whereas irrational numbers are non-terminating, non-repeating decimals. Non-repeating decimals. Well, you're probably familiar with one that you've talked about year after year, pi, because pi doesn't terminate and doesn't repeat, and there's no pattern to it. It just works out to be 3.1415, blah, 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 blah. But there's tons of others irrational numbers. There's actually an unlimited, an infinite number. The square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, and so on. What you might be noticing is that I skipped all the perfect squares. So any root that is not a perfect square is actually an irrational number. And I did give you some cute little examples of different numbers. So these are examples of irrational numbers. We've got our rational numbers. Look, -2 3/10. That can be expressed as a fraction. 0.5, it's a terminating decimal, so it can be written as a fraction. Integers, but I said integers had to be whole. Well, remember, if you evaluate the number, that becomes -5, so it would be an integer. All right, so, So we're going to talk about fractions. So fractions, we said, are called we can call them, they're in the family of rational numbers. Okay? And we have some parts. The numerator is the top and the denominator is the bottom. But there are some fractions I really think are important for you to know, okay? Obviously, you should know 1/4, 1/2, and 3/4 as decimals. So point is 0.25, 0.5, and 0.75. Some other ones that are really important: 1/3, 0.3 repeating, and 2/3, 0.6 repeating. And look at that. 1/3 is 0.3 repeating, 2/3 is 2 times it, so 0.6 repeating. The other ones are 1/5. 1/5 is 0.2, or 20%. So what do you think 2/5 is? Well, hopefully you're saying 2/5 is 0.2. 3/5, I'm sorry, it's 0.4. 0.4. 3/5, 0.6. 4/5, 0.8. I want you to think about what you notice with those numbers, and we're going to talk about that tomorrow. All right, it's also important for us to understand where numbers lie on a number line, okay? Where rational numbers lie on a number line. So if this is 0 and this is the number 1, and I've got a couple breaks in between, where is 1/2? Well, I think you know that 1/2 would be right in the middle. In relation to 1/2, where's 1/3? Is it bigger or is it smaller? Well, hopefully you realize that 1/3 is smaller, and then 1/4 is even smaller than that. So as the denominator gets bigger, the fraction actually gets smaller. All right, what about 2.6 repeating? Well, we said 0.6 repeating was 2/3, so 2.6 repeating would be 2 2/3. All right, so here's 2, here's 3, and then if I break it into thirds, 2 2/3 would be right about here on the number line. All right, now let's look at irrational numbers. How do root 17 and 3.8 compare? Okay, now I think in your notes it says 3.5, so let me change that, okay? How do root 17 and 3.5 compare? Well, when you think about an irrational number, because it's non-terminating, non-repeating, it's important for you to be able to estimate where it would be about on a number line. So I use perfect squares to help me. All right, so we talked about perfect squares when we talked about the locker problem. So let's just remember our perfect squares: 1, 4, 9, 16, 25, 36, and so on. It means that their square roots, the square root of 1 is 1, the square root of 16 is 4, the square root of the square root of 9 is 3. The square root of 81 is 9, and so on, right? So if I think about this, I know that root 17 is right after root 16, okay? Right? So I know that it's a little bit bigger than the number 4. So I know that this number is bigger than 4. So if I compare 3.5 and the number 4, well, I know 3.5 is less. So if I compare 3.5 and root 17, I know that 3.5 has to be less because 17 is bigger than the number 4, which was a perfect square. All right, I'm sorry. And going back here, I kind of got tongue-tied. The square root of 9, if I take the square roots of each of these numbers, then I would get the square root of 4 would give me the number 2, right? The square root of 9 would give me the number 3. The square root of 16 would give me the number 4, and so on, 5 and 6. All right, let's try another one. Oops. The square root of 71. The square root of 71. Well, okay, I have to think about the closest perfect squares to that. And I like to stay with consecutive. Consecutive numbers are numbers that are right next to each other, like 1 and 2, 5 and 6. Those are consecutive numbers. So I like to go with consecutive squares. So I know that the square root of 64 is 8. And it's a little bit smaller than 71. So I go to the next consecutive square, which would be 9 squared, which is 81. The square root of 81 is 9. So I know that 71 is somewhere in between 8 and 9. Now, could we estimate? Well, it's 10 units away from 81, and it's, what is that, 7 units away from 64. So I know it's a little bit closer to 8 than it is to 9, so maybe I could say 8.4. So that would be a good estimate of square root of 71. Okay, so that's a great method for you if you want to estimate where a radical or a root is, okay? And I always, again, try to work between two consecutive numbers or two consecutive square roots. All right, so the last thing that we need to talk about today is the properties of algebra. Now, every year you usually talk about the properties, but I want to put them in algebra terms. So the commutative property is like when Dad commutes to and from work. The commutative property of addition, okay, of addition. I'm going to do addition and multiplication because these properties apply to addition and multiplication. It says that x plus 4 is the same thing as 4 plus x. Now you got to know that doesn't work for subtraction. X minus 4 does not equal 4 minus x. So these properties again apply to addition and multiplication. A little bit trickier is that, when you were younger, you were told that 2 times 3 was the same thing as 3 times 2. In algebra, something like this could happen. X plus 2 times x minus 2 is the exact same thing as x minus 2 times x plus 2. I'm taking two quantities and I'm multiplying them. So it doesn't matter which way I do it. I could have the x plus 2 first or the x minus 2 first. So that's the commutative property of multiplication. The associative property basically means that you can associate with different people. When at school, Josh often associates with Tanner. When at home, Josh often associates with Kevin. So I could, if I have with addition, I could do 3 plus 4 plus 6 and 3 plus 4 plus 6. Depending on how I see this, I could associate the 4 and 6 and add them together. Or I could associate the 3 and the 4 and add them first together to make it easy for myself. It really depends on what you feel the most comfortable with. Same thing with multiplication. I'm allowed to associate different numbers. So if I had like 3 times 7 times 10 and 3 times 7 times 10, well, depending on how I see it, I could do 3 times 7 and then multiply it by 10, or I could do 7 times 10 and then multiply it by 3. That's the associative property of multiplication. All right, so the identity property, important. The fingerprints revealed the thief's identity, okay? That means, how do you get back to yourself? Well, with addition, how do I get A? What can I add to A to get A? Well, the only thing you can add to A to be left with A is a 0. And with multiplication, think about, how do I get from A to A using a number? Well, I'd be multiplying by 1. So these are called it's called the identity property. And sometimes with identity in algebra, you'll get answers like this, 12 equals 12. If you see that 12 equals 12 or 7 equals 7, and that's what you end up with when you simplify an equation, well, guys, that means that the solution is all real numbers. And we call it the identity. And again, there's that symbol that we use to indicate all real numbers. Every single number from infinity to negative infinity. All right, just a few more. All right, the inverse property. I love this property. The inverse property basically for addition basically says that you have to undo an operation. So if I tell you that A, the way for me to undo A would be to add a negative, its opposite to it. And I would end up with 0. This is called the additive inverse. The additive inverse. And basically when you're doing the additive inverse, you're really just doing the opposite of the number, okay? Whereas with multiplication, slightly different, the multiplicative inverse, you're actually multiplying by the reciprocal, okay? So with the inverse of multiplication, you're ending up with the number 1. With the additive inverse, you're ending up with 0. And again, with the multiplicative inverse, you're doing the reciprocal. We're going to work a lot with reciprocals this year. Okay, last thing, the distributive property, our favorite. All right, the distributive property basically says if I'm given, let me switch colors so you can see it better, 2 times x plus 5, then you can multiply 2 to both terms in the binomial. So the 2 gets multiplied to the 2 and to the 5, and you would get 2x plus 10. One thing I want you to be really careful of, if I give you something like this, oftentimes kids want to subtract those numbers, but remember, with proper order of operations, you actually have to multiply first. And the distributive property, there's a hidden multiplication there. The distributive property does mean to multiply. So you'd have to multiply that first and get 3 minus 2x minus 2, making sure that that negative 2 gets distributed, and then combine the like terms to get 1 minus 2x. All right, guys, thanks for your attention today, and have a great night.